Hi everyone, welcome back to Dave's Math channel. This is my sixth video in a sub-series on limits and a series on calculus. And I think I'm only going to have one more video on limits after this one. But today I'm going to talk about infinite limits. Anyway, let's begin. What is an infinite limit? Well, there's two types of infinite limits when we're talking about real value functions. There's limits that go to plus infinity, which we usually just write as infinity, and then there's limits that go to minus infinity. And there's also one-sided and two-sided limits. And these definitions are pretty vague. These don't involve delta. The real definitions involve, remember we were using epsilon and delta before when we were doing just ordinary limits. Now we're going to use n and delta, where n is a large number. And again, delta is a small number. But anyway, this just kind of gives you a taste of what's coming up. So here's the real definitions, and there's actually six different types of infinite limits here. So there's one-sided infinite limits, and those can be either right-hand or left-hand infinite limits, just like we had for finite limits. So here's the definitions. Let me just read them. So we say that the limit as x approaches a from above of f of x is plus infinity if for every positive number n there exists a positive number delta such that f of x is greater than n when either x minus a is less than delta, which kind of makes sense if you think about it. It just means that the function's approaching infinity on the right side of x equals a, because no matter how big n is, you can make f of x bigger if you move closer. So that's what's going on. And then similarly, we can define the limit from below. We just do it the same way, except this time we're not taking x minus a, we're taking a minus x because that's positive. And anyway, I might have written this down wrong. Oh no, actually, we have the limit as x goes to minus infinity. So we have two right-handed infinite limits. Remember, there's the limit that goes to plus infinity, and there's the one that goes minus infinity. Exactly the same definition, except that we're letting the function has to be less than minus n instead of greater than n. And then we have the same kind of thing for left-handed infinite limits. We're just approaching a from below this time. And then we have two-sided infinite limits. And those, it doesn't matter whether we're approaching from above or below. We either get a limit of plus infinity or minus infinity from both directions. And there's examples of all these different kinds of infinite limits, and I'll show you some. So now I've given you the definitions. Now I'm just going to show you some examples. And this is a pretty easy example. It's a good one to start with. This is just, the kind of standard hyperbola y equals 1 over x, which I'm sure you guys have seen before. Has two asymptotes. One's the x-axis, the other's the y-axis. And I think you can kind of see, intuitively that this function approaches either infinity from above or minus infinity below as x approaches 0. So anyway, that's pretty intuitive from the graph, but we still have to prove that. So we use the n delta definition. So we just let n be an arbitrary positive number. This time we let delta equal 1 over n. And then we note that if x is positive and less than delta, which is equal to 1 over n, then f of x, which is 1 over x, is greater than n, which proves that the limit as x approaches 0 from above is plus infinity, is claimed. And the proof for the other side, for the left-hand limit, is pretty much the same proof. It's just this time we have to show that it's less than minus 1 over n, which it is by the same token. We let um, So anyway, that's how we prove this, and that's a pretty simple example. And then this one actually has a two-sided limit. This is 1 over x squared. So this one, it doesn't matter whether we approach it from above or from below. We're always going to get plus infinity for the limit. And I think that's pretty easy to see. This time we let delta equal 1 over square root of n. And then we just note that if the absolute value of x is less than delta, which is 1 over square root of n, then f of x, which is 1 over x squared, is going to be greater than n. So that proves this case. That's a two-sided limit. And I'm just going to finish with this example. This is a pretty complicated example. Like I said, these epsilon delta, or in this case, the n delta proofs, can be pretty messy sometimes. So I'll just give one example. There's actually 4 limits for this function. This is a pretty complicated function. This is f of x equals 1 over the quantity x minus 3 times x plus 2. So you'll notice that this function has 2 vertical asymptotes. It has one at x equals minus 2 and another at x equals plus 3. And again, these are going to be one-sided limits for both cases. So there's actually, if you wanted to, you'd have to derive all 4 limits. I'm not going to do that. I'm going to derive one of the 4-sided limits. So let's show that the limit as x approaches 3 from above of f of x is equal to plus infinity, which it looks like from the graph. You can just see that, this right branch of this function, as it's approaching 3, x equals 3 approaches plus infinity. That's pretty clear. So how do we prove this? So we have to use this n delta argument, and it's not that easy. There's 2 cases you have to look at. Let's look at the case first where delta, we're assuming that delta is less than 1. That's how we'll start this proof. So that means that x is going to be between 3 and 4. And then we can just write x is 3 plus delta, where delta is less than 1, and then we can plug that in to the formula for f of x. And if you do that, you'll find that f of x, you can rewrite it as 1 over delta times 5 plus delta. 5 plus delta is just x minus 2 in this case. If I did this right, I'm not sure. X plus 2. Yeah. And then so what delta over 5 plus delta, the thing you should note here is since delta is less than 1, that means that 5 plus delta is less than 6. So that means that 1 over delta times 5 plus delta is greater than 1 over 6 delta. And now we're in business because this is going to be greater than n as long as we let n equal 1 over 6 delta. Right? Is that right? Yeah. I'm not sure how this works, but yeah, we found a form for delta. As long as delta is n over 6, I think it works. But then there's another case we have to consider, the case where n is less than 1/6. In that case, it turns out that we can let delta equal 1. Because if we let delta equal 1, then we find that f of x is going to be greater than 1/6 in this case. Remember, x is now greater than 4, so f of x is going to be 1 over 6 times x minus 3, which is, well, actually, we're letting delta equal 1, so this is going to be 1 over 1/6, which is greater than n as long as n is less than 1/6. So that takes care of the second case, and that completes the proof that the limit as x approaches 3 from above of f of x is plus infinity. Pretty messy proof for a pretty obvious statement. That's why I don't really like these epsilon delta and delta proofs, but you have to do a few of them when you're learning limits, unfortunately. You won't have to do too many more of these, so don't worry too much. But anyway, that completes my my lesson for today on infinite limits. I hope you enjoyed it. Thank you for watching. Long live math, and I'll see you guys next time. Bye.